Mersenne primes. One unsolved problem in mathematics concerns whether or not there are infinitely many Mersenne primes. In order to understand what a Mersenne prime is, consider the expression 2 to the n minus 1 for a non-negative integer n. A number of this form is called a Mersenne number. These are named after Mersenne, a French mathematician. For some prime number values of p, the value of the whole expression is also a prime number. For example, plugging in p equals 2, the expression evaluates to 2 to the power of 2 minus 1, which is the prime number 3. A prime number of the form 2 to the p minus 1, where p is also a prime number, is known as a Mersenne prime. As it turns out, if p is a non-negative integer, then it must be a prime number for 2 to the p minus 1 to equal a prime number. However, there are some prime number values of p that do not produce a prime number. For example, if p equals 11, then the expression evaluates to 2047, which is a composite number with factors 1, 23, 89, and itself. As a result, you can't just plug in Mersenne primes themselves for p in order to keep getting new Mersenne primes forever. Indeed, there is no consistent, reliable formula for generating Mersenne primes. Finding new ones primarily comes down to using guess and check computer algorithms. Currently, only 51 Mersenne primes are known, with the largest one being 2 to the power of 82,589,933 minus 1. Incidentally, this is also the largest known prime number overall. Based on our computations, Mersenne primes seem to be exceedingly rare among the Mersenne numbers. However, whether or not they eventually stop remains a mystery. Perfect numbers. A perfect number is a positive integer equaling the sum of its proper divisors, which are the number's divisors other than the number itself. For example, the proper divisors of 6 are 1, 2, and 3, and 1 plus 2 plus 3 equals 6, so 6 is a perfect number. The next few perfect numbers are 28, 496, and 8128. There are two main unsolved problems relating to the perfect numbers. One of them asks whether or not there are any odd perfect numbers. Odd numbers tend to miss out on divisors thanks to not being divisible by 2, or by any multiple thereof. Currently, all of the 51 known perfect numbers are even, not odd. However, much progress has been made in regards to this problem. Mathematicians have come up with an incredibly long and strict list of rules that an odd perfect number must follow, if such a number exists at all. Going over the whole list would take all day, but needless to say, odd perfect numbers must be either very rare and special, or completely non-existent. In general, mathematicians guess that the latter is true. The set of conditions required for an odd perfect number just seems far too restrictive. As English mathematician James Joseph Sylvester put it, a prolonged meditation on the subject has satisfied me that the existence of any one such odd perfect number, its escape, so to say, from the complex web of conditions which hem it in on all sides, would be little short of a miracle. The second problem about perfect numbers asks whether there exist infinitely many of them. There are some known facts related to this problem. For example, the Mersenne primes are closely related to the perfect numbers. Consider the expression 2 to the power of quantity p minus 1 times quantity 2 to the power of p minus 1, where 2 to the power of p minus 1 is a Mersenne prime. In that case, no matter what Mersenne prime we have, this expression always gives us an even perfect number. If p equals 2, our Mersenne prime is 3, and this expression evaluates to 6. If p equals 3, our Mersenne prime is 7, and this expression evaluates to 28, and so on. This fact was proven by the Greek mathematician Euclid. Conversely, given any even perfect number, we can find the Mersenne prime that would have yielded it when using this expression. In other words, there exists a bijection, a one-to-one correspondence, between the set of perfect numbers and the set of Mersenne primes. This was proven by Swiss mathematician Leonhard Euler. In honor of Euclid and Euler, this theorem is called the Euclid-Euler theorem. Because of it, as soon as anyone finds out whether or not there are infinitely many Mersenne primes, we will also know whether or not there are infinitely many even perfect numbers, and vice versa. Rational distance problem. In geometry, a plane is a flat 2D space that extends to infinity in all directions. Basically, an infinitely large sheet of paper. Imagine a unit square, a square with sides length equal to 1 unit, living in this space. The rational distance problem asks, does there exist a point in the plane a rational distance away from every vertex of a unit square? To elaborate, suppose that this plane has a Cartesian coordinate system, the usual xy coordinates you may be familiar with. For simplicity, we'll place this square's vertices at 0, 0, 0, 1, 1, 0, and 1, 1. Now, for this problem, pick any point in this plane. Calculate the distance between this point and each vertex of the unit square. The distance between 2 points, x1, y1, and x2, y2, can be calculated using the distance formula. D equals square root quantity x2 minus x1 squared plus quantity y2 minus y1 squared. For the chosen point and the 4 vertices of the unit square, the goal is to have every one of the 4 distances be a rational number. Despite the apparent simplicity of this task, no one has succeeded at it yet, nor has anyone proven that it is impossible. One option is to examine regular polygons of unit side length other than the square. The simplest example is the equilateral triangle, for which we know that a point can be chosen to result in all distances being rational. This also holds for the regular hexagon. However, the answer for squares, octagons, 12gons, and 24gons remains unknown. All remaining regular polygons, the answer is known to be no. If you want to try solving some math problems yourself, you'll probably want to train your mathematical skills. For that, there's no better place to start than today's sponsor, Brilliant. Brilliant is a learning platform that emphasizes hands-on education. Lessons let you play with the concepts yourself rather than just seeing them, a method shown to be far more effective than simple lecture videos. Brilliant features thousands of interactive lessons in math, AI, programming, and data analysis, all created by top teachers, researchers, and professionals from universities and companies like MIT, Caltech, Duke, Google, and Microsoft. With simple short lessons you can do at your own pace, you can build your knowledge every day. To try everything Brilliant has to offer for free for a full 30 days, visit brilliant.org/thoughtthrill or click on the link in the description. You'll also get 20% off an annual premium subscription. Moving sofa problem. Imagine a hallway 1 unit wide with a 90-degree L-shaped bend. You want to slide some kind of shape, let's say it's a sofa, from one side of this bend to the other. What is the maximum possible area that such a shape can have? Whatever this maximum value for the area is, it is called the sofa constant. We can start with a half disk of unit radius, where a disk is the region enclosed by a circle. The unit disk has an area of pi, and half of that is pi over 2, about 1.57. This gives us a simple lower bound on the sofa constant, but we can do better. In 1968, British mathematician John Hammersley proposed a sofa roughly in the shape of a telephone handset. This sofa has an area of pi over 2 plus 2 over pi, about 2.207. Later sofas have surpassed this number, with the current record being 2.2195, believed to be close to the true sofa constant. Upper bounds on the sofa constant have also been obtained. Hammersley found an upper bound of 2 times square root 2, about 2.828. Later in 2018, Yoav Kallis and Dan Romick lowered this to about 2.37. Their approach involved using computers to rotate the hallway around the sofa, not the other way around. Inscribed square problem. A curve is closed if it loops back on itself, and it is simple if it doesn't cross over itself. A simple closed curve in a plane is called a Jordan curve. A polygon is inscribed in a curve if all of its vertices are on the curve. The question is, does every Jordan curve have an inscribed square? We can start with some simple examples of Jordan curves. A circle is a Jordan curve, and it has infinitely many possible inscribed squares. A square itself is also a Jordan curve, and infinitely many inscribed squares can be found in this curve as well. As for triangles, an obtuse triangle has exactly 1 inscribed square, a right triangle has 2, and an acute triangle has 3. In the general case, the problem has proven to be difficult. However, some special cases have been proven. For example, in 1916, Arnold Emch showed that a piecewise analytic curve must have inscribed rhombuses, and at least one of these rhombuses is a square. Also, it has been shown that all symmetric curves have at least one inscribed square. Another case involves an annulus, the region bounded by two concentric circles, where the outer radius is at most 1 plus square root 2 times the inner radius. If the Jordan curve is inscribed in such an annulus and separates the annulus's inner and outer circles, then a sequence of squares leading to a square inscribed in the Jordan curve can be found. Ramsey theory problem. Ramsey theory is a branch of combinatorics named after British mathematician and philosopher Frank P. Ramsey. It is primarily focused on the size of mathematical structures. One problem is as follows. Consider the vertices of an n-dimensional hypercube. 1D is a line segment, 2D is a square, 3D is a cube, and so on. Draw edges from every vertex to every other vertex, forming what is known as a complete graph. Each edge can be colored either red or blue. Depending on the number of dimensions n, it may be possible to color these edges so that if you take the complete graph of 4 vertices in the same plane, not all the edges are the same color. This complete graph can be visualized as a square with the diagonals drawn in. What is the smallest number of dimensions in which this is possible? Lower and upper bounds for this problem have been obtained. In 1971, American mathematicians Ronald Graham and Bruce Lee Rothschild found a lower bound of 6. In 2003, Jeffrey Exo improved this to 11, which was later improved to 13 by Jerome Barkley in 2008. As for the upper bound, it can only be reasonably expressed using operations known as the hyperoperations, which extend the usual operations of addition, multiplication, and exponentiation. The most famous upper bound found for this problem is a number called Graham's number, which once held the world record for the largest number used in a serious mathematical proof. Graham's number is too large for an ordinary decimal representation of it to fit into the observable universe, even if each digit is only 1 Planck volume, and even that astronomically undersells its size. In any case, the current upper bound is a much smaller number that looks like this.